so we could spotlight. Okay, thank you. So I think we can start today's symposium. Professor Sacha, please.
Okay, all right. Good morning, everyone. Good morning, good afternoon, everyone. Welcome to the second day, session 3 of the Carbon Neutrality Symposium, organized jointly by Zhejiang University, the University of Sydney, National University of Singapore, and Indian Institute of Technology, Madras. We had a great day of deliberations yesterday, and on the same note, we'll continue today. I am Professor Satya Seshatri from the Department of Applied Mechanics at IIT Madras, and I also lead the Energy Consortium at IIT Madras, working to bring together researchers such as yourselves and industry towards developing meaningful solutions for the transformation to a low carbon future. On the same note, we have quite a set of exciting speakers today, so let me quickly get on without wasting further time. So first up, we have Associate Professor Girish Lakwani, who is the Deputy Director of ARC Center of Excellence in Exciton Sciences at the University of Sydney Nano Institute. Professor Lakwani received his PhD from Eindhoven and his master's from IIT Kanpur. So his research is focused on optical and time-resolved optical spectroscopy to study the origin and evolution of optoelectronics. Here, he's there to talk about organic solar cells and optical cavities. So, Professor Girish.
Thanks a lot for your kind introduction, and I'm excited to be here. Let me share my screen, and please do let me know if you can see the screen. Just give me a second. Can you see my screen?
Yes. Yes.
Perfect. Well, thanks a lot for your kind introduction. And some of the things that I'm actually pretty excited and I want to show and discuss with you is organic solar cells and cavities. And this is, of course, the session is going to be talking a lot about solar cells. And this is our take on what we can do towards basically providing solutions for harvesting energy in a much more productive fashion, using organic materials which are far more flexible, easy to make, and some things that we have a little bit expertise on, and we want to kind of explore new ideas around this. So one of the things before I get started, I quickly want to give you a snapshot on what we do and what we care about, because that kind of sets up a tone on what are our motivations behind it. Of course, one of the things which, as during the introduction was mentioned, our research actually very much focuses on evolution of optical properties, and we want to understand why certain molecules behave better than they do. And one of the applications we look forward is in organic solar cells, LEDs. We are also very interested in low power driven electronics, because there's one thing to harvest energy, but at the same point, we have to be creating devices that use low power to be able to judiciously use energy, which we actually use a lot excessively sometimes. So we are looking at research from both facets. So today, one of the things which I want to talk to you about is what we do in photovoltaics, especially in organic solar cells. I believe that anytime when we want to kind of realize an excitonic device, one of the things which we are looking for is, can we actually control the flow of energy? And when we talk about flow of energy, I often use terms exciton, which is basically when light shines on a material, you create electron-hole pairs. And in organic materials, they are tightly bound because organics have low dielectric constant. And these tightly bound entities is what I call excitons. Of course, you have to break these excitons to get free charges. And that's essentially what and how we work towards organic photovoltaics. I know that many of you would have known this already, but thought to just give you a quick snapshot of that. Some of the things which we actually really care about is, can we control energy flow? Can we figure out how can we not only harvest energy, but can we manipulate it? Can we actually get meaningful work done with minimum losses? This graph, if maybe I'm I missed the last session, so I don't know if this graph has already been shown or will be shown. But this is essentially the best research cell efficiency so far. And you can see there are plenty of technologies shown all over here, right from going from silicon, 3-5 semiconductors, perovskites, which have really picked up. And my couple of speakers after me are going to talk about perovskites as well. As I've highlighted here is, of course, the yellow section, which is organic solar cells, which is what we care about, and which is where our key core research interest is. And off lately, in the last 5 years, it has taken off quite a lot, with high efficiencies pretty much rivaling perovskites, and other devices have already been seen. However, one of the things in organic molecules is that when you make these thin films, they're amorphous in nature, and something we want to understand what role that plays on different photophysical processes in solar cells. And we believe that if we can understand these photophysical processes, that's from where you get right sort of materials and solutions for kind of devices we are interested in. This is typically how organic solar cells work. Just quick snapshot, you shine light, you create excitons which move towards donor-acceptor interface, which is where you dissociate them and you can get off free charges. And this is essentially shown over how the processes work. You create excitons, you then create a charge transfer state, which you get into free charges. Now, in our lab, we have already been working on non-Fullerene acceptor solar cells because, first of all, fullerene is fairly limited and very difficult to synthesize. So one of the things in the community has happened is we are pushing towards non-Fullerene acceptors, which are easier to make, offer you much better control over organization of materials. And again, the thing what we have done is in our lab, we have already shown high efficiency devices, but that's not what we are here about. Here is the idea is how can we make these materials better? How can we actually help achieve much out of the same solar cell without necessarily doing empirical study of mixing, matching donor acceptor molecules. So one of the things we were interested in is, can we actually change the state, the potential energy state of materials without changing the material? And this is something which I get super excited about because this is where I'm going to talk about optical cavities. So if you take any material and you put it in a cavity, which is nothing but two reflective mirrors, you can couple the molecule with the cavity. And what you would see is once you reach to a resonance condition where the standing wave inside the two mirrors matches with the energy of your material, what you would see is that you will split energy levels. And once you split energy levels, effectively you have changed the potential energy surface of the material without changing the material itself. So what that gives you is a big handle on essentially changing or driving different photophysics, different material properties altogether. And this is often we do. One of the examples is if you pick up a material, put it in a cavity, you can see that the absorption, for example, starts splitting and you can split the peaks. And that's how you can show that you've indeed achieved strong light matter coupling. And that's what we do for a lot of material dyes. We actually put them in the cavities and we see how we can manipulate their optical properties, how we can manipulate their energy, which is then we can use that to drive different kind of photophysical processes. Over here, because of short of time, I'm just going to give you one example on how we do that, just to give you a bit of a flavor. One of the things which we do is we want to see there are solar cells community, which is actually making new kinds of materials, new devices. And over here, we are very interested in how we can kind of use different device geometries to optimize them. And one of the things which we do is we put them in optical cavities and change the potential energy surface. We perform these very complicated experiments, not that I'm going to go into depth, but the idea is that you make these devices, typical architectures using typical perylene devices and polymers which are conjugated in nature, which give them semiconducting properties. And you can make a lot more measurements. Here they're shown essentially where you can see these photonic fringes. So you're seeing basically patterns, which is where it's coming from the photonic cavity. And what you're doing is not only enhancing the absorption, but you're also changing the potential energy surface, which is shown over here. And what we see effectively is that we can kind of split the energy states just by doing putting these molecules in cavity. And what we do is we actually increase the open circuit voltage, which is essentially a measure of power that we can derive from these solar cells. So essentially what we have done is we have taken nothing but we have taken organic solar cells, which are very good working devices, put them in cavities, And what we have essentially done is we have changed the whole diagram that you show over here. Here you have these different rates associated with different processes. Now, if you put things in cavity, you split it, you change all these processes. You optimize all the processes because you get better charge transport and you can get much lesser losses. So essentially the idea is that using cavities, using strong light matter coupling can not only make devices better, but can also drive new photophysical phenomena from the similar materials. So a lot of carbon-based materials that we explore, the idea is that can we get more out of it? And that's essentially what the key message I want as a takeaway is essentially you can demonstrate the strong coupling between different conjugated molecules, organic molecules. You can use them towards low power driven electronics. You can actually make much more efficient light emitting diodes and lasers out of it, which we have shown in our labs as well, which I didn't discuss today. Of course, you can actually put solar cells in them and can increase voltage without essentially changing the material, which is quite a plus point because then you minimize the use of different kind of materials, rather use the same kind of combination, but change the geometries. And again, there is an active area in how we can actually use to modify chemical processes and catalyze reactions. It's a whole area of photocatalysis that actually emerges from this field. So of course, that was a quick snapshot on what we do, fairly a little bit technical, so sorry about that. But again, that was just to give you an idea on what we do. Of course, this is not the work done by us. There's a huge group who does that, and we have very good collaborators and funding from the Australian Research Council, and of course, a lot of facilities supported by Sydney Nano. And thank you for your kind attention. I hope I made it in time in 10 minutes that was given to me.
Thank you. Thank you very much, Professor Girish. That is quite wonderful and very interesting work. And I do have some questions, but I request the audience to reserve the questions to the Q&A. Right up, we have Dr. Nikhil Tambe from IIT Madras, who is the CEO of the Energy Consortium. And he's going to talk to us about the transition to a low carbon future through a consortium approach. Dr. Tambe headed the Ohio State India Gateway. Prior to that, he was a researcher and a technology leader at GE Global Research and Eaton. He holds a PhD in material science and tribology from Ohio State. And we have Dr. Tambe to talk about the Energy Consortium. Dr. Tambe.
Thank you very much, Satya, and through you, thank you very much to the entire organizing committee. I joined in yesterday as well, and I'm looking forward to the rest of the day today. I think it's wonderful to actually hear from across the APAC community. There are a lot of challenges that the countries in this region are facing, which are very similar to each other, and even the technology approaches leave us with a lot of thought in terms of how we could leverage what we are learning in one corner of APAC and use it elsewhere. Over here in India, I mean, we've seen a fantastic decade of solar dominance. I mean, it was, of course, wind and solar together, which is helping India get into the renewable energy domain more and more. I'm showing a picture here on the slide, which is an extension of our campus. It's known as the Research Park, the IIT Madras Research Park. And what you will obviously notice over here is how we are trying to harness not just the solar energy, but the potential that we have in terms of the technology development just across the campus, and using this as a test bed, using this campus as a test bed for us to test many of these technologies, which are probably going to help us enable the transformation to what we call as the low carbon future. Okay, I mean, just in terms of some numbers, this is a 1.2 million square feet of office space, and our goal is, to maximize the use of electric energy on this part of the campus through the solar panels that you see in the picture, but as well as wheeling in some solar and wind energy, and therefore reduce our dependence. The second aspect also, I mean, in the context of the talk today, which I want to highlight is, as we think of enabling the transformation, we have to think of how we go about energy efficiency, the energy optimization, and then energy transition to the renewable sources. So that's something that we are trying to envision. Now, energy and research in energy is not necessarily new at IIT. So what I'm trying to show here is 7 energy research initiatives across IIT Madras. This is work that has been happening for maybe the last couple decades or so. And we've consolidated all that work into these 7 energy research initiatives. What we have done recently is now we have announced an energy consortium. The idea is to bring together not just the faculty consortium and the academic consortium that we have built this on, but also pull in a lot more industry focus and a lot more government focus. And with government, I of course mean not just the funding agencies, but also the policy focus. So our objective is, how can we resource and repurpose these 7 research centers to develop any new grand challenges that are coming our way. In India in particular, and of course across the world, there's a lot of focus right now on hydrogen economy. And we have large faculty groups working across these centers. For example, the photo and electrochemical energy group is focused on electrolyzer development. So their exclusive focus is how to get green hydrogen. Now this is very relevant and important for us because we just had a government policy rollout a couple weeks back, and that has set us to decide, what kind of dollar targets that we want to put on the hydrogen that we are going to produce through these green electrolyzer means. There are other groups in this that are focused on, therefore, the other aspects of it. So we have a renewable energy systems group, which does a lot of techno-economic analysis that allows us to think of all the technologies in terms of how are they going to fit into the economical bandwagon, which of these are actually going to be commercially viable, and therefore also the time frame that it's going to take for some of these technologies to become commercially viable. Okay. There are some groups which are working downstream. So, if I continue the same hydrogen aspect, we have a group which is focused on how can we use hydrogen as a alternative fuel. There's already a lot of work on sustainable aviation fuels, and either blends or pure hydrogen could be a future fuel that is being worked on by this group. Now, this group actually houses one of what we call as a national asset. It's the National Combustion Conversion and Research Lab that we have here at IIT. So we are really trying to leverage the infrastructure that already exists, but try to tackle these new grand challenges that are coming our way. In passing, I also want to talk a little bit about the carbon capture and storage. Although I mentioned a lot about the renewable energy so far in what I described, there is obviously a significant need to reduce the current emissions that we have, as well as the emissions that have already happened over the last few decades. So there is a lot of interest that we have on how can we utilize our expertise in carbon capture. Some of the recent estimates suggested that there's about 200 million tons of carbon dioxide that we can sequester today. And there's about 32,000 million tons that we need to. So clearly there is a long way for us to go. While we focus on carbon capture, we are also starting to think critically on the utilization piece. Can we make some useful fuels and chemicals? Particularly in our country, there is a strong need for chemicals such as ammonia. We import a lot of these. So what if we can combine our desire to reduce the emitted carbon and also to meet our economic needs in terms of chemicals such as these? So those are the focus areas for this group over here. Ultimately, when we think of the consortium approach, we think of two things. One is if we are able to devise solutions for India, just because of the fact that the scale that we need to deploy these solutions in a large country like ours, we believe that if these solutions are successful economically, there's a very easy chance that these will be successful in other parts of the world. So that's the driver and the motivation for the same. We are collaborating heavily globally with many of the countries in the APAC region in particular, and the collaborations are on 3 dimensions. So of course, technology and innovation, which will lead into products and applications. So that's the clear central goal. Can we leverage all the research centers that we have and go towards applications? For that, of course, we are collaborating with industry. That's where the industry partners come into picture very clearly for us. But while we do that, we don't want to lose our sight on how are we going to switch lifestyles? How are the end users going to start adopting these applications? I just talked about the sustainable aviation fuel. If we don't have people choosing, flights which use those fuels in future, then we are going to have to worry about, how do we make these behavioral changes happen? So there's a large effort underway as part of the consortium on how to drive societal impact. We are working closely with the government on this, but we are also working closely with the users of a lot of these applications. which may be, small businesses, medium and small enterprises, to end users, to the society at large. Right. So we feel that these two are critical pillars, one to develop, the second to imbibe and make sure that the society absorbs this. And while we do this, we are very clear that we have to focus on this effort as how can we cultivate future energy leaders. I mean, if I think of 2030 or even 2050 kind of deadlines, what we know as a university, the students who are in their undergraduate education today are going to be the leaders in 2030. So they are going to live in a world which is more renewable energy world. Are they prepared for that? Are they prepared in terms of making decisions at that level? And they should be. So that's one of our clear endeavors on how do we use the energy consortium and our traditional expertise to cultivate such leaders. So that's a little bit in the short time that I had today. Of course, this is a very brief introduction, but I hope this opens doors for collaboration. We are actively looking at collaborating across with different countries, with academia as well as industry and governments. So look forward to hearing from others and trading some thoughts on these topics. Thank you very much, Professor Satya, for the time I had.
Thank you. Thank you very much, Dr. Nikhil. Now I have the pleasure of requesting Professor Armin Abril, I hope I spelled the name correct, to talk about the solar PV activity and what's next for solar PV in NUS and the world at large, the latest trends and activities. Just to give you a brief background, Professor Armin heads the Solar Energy Research Institute of Singapore, and he's also a tenured full professor in the Electrical and Computer Engineering Department. His research is primarily focused on PV materials, devices, and modules, and I hope Professor Armin takes us through a nice journey. Professor Armin?
Okay, thank you very much. Can you see my
Yes, we can see your screen. Yes.
Okay. So, I would like to give you the latest trends in solar in the world and then what we are specifically doing here at NUS in Singapore. This is a photo of Singapore. It's an Asian megacity. And there is no hinterland. That's one problem we have here in Singapore to solarize the nation. Where do we put all these solar panels which we need? And of course, the solar panels, which I'm sure you have seen these things, right? The solar cells are here bundled together behind a glass sheet and interconnected, say 60 or 72 of them to create the required voltage for the grid. Now, there is a solar revolution happening actually quite quietly. It has been going on for 40 years. And it seems it's unstoppable. And today we are now at 170 gigawatts of solar panels which are sold globally. Just to put that in perspective, that is 500 soccer fields every day. 500. And as you can see, if the story continues, within 10 years, before 2030, we will reach 1,000 gigawatts, 1 terawatt per annum global deployment. And so that's then where solar will take over the energy world. At those deployment levels, that's 3,000 soccer fields every day. Solar is unstoppable and will transform the global energy system together with wind power, basically. And that's what we are all working on. It will be $1 trillion industry. We need these young people who make this happen, right? Lots of researchers, deployment, system developers. It's an amazing technology, and I think the time is now right for becoming significant globally. The next factor of 10 will be huge. It will bring us from 3% global contribution in electricity to 30, right? And then we are the biggest in the world. To make this happen, we have to make these solar panels better in efficiency. So that's the bottom line you see there, the plan over the next 10 years. This is the global solar industry. And you can see we are today at about 22% panel efficiency, the leading products. And then we want within 10 years, we want to go to say 24. That might seem humble, but this is an energy technology which will power the world. These panels have to be robust, reliable, last for 20 years on the rooftop. So you cannot just change too many things every year. It's a little bit like smartphones. You go from iPhone 12 or whatever to iPhone 13, and the technological progress happens via hard work and sweat by an army of researchers, engineers, and technologists. And then if things go according to plan in 2026, something amazing will happen. We will switch from a single junction solar cell, like today, that's silicon, to something which has two junctions behind the glass sheet, like two hearts, two engines in the solar panel, and then you get higher efficiency. So the dream is by 2026, in 4 years' time, the world, we introduce the first tandem solar panels into the global market, and then of course the efficiencies will also go up over time. And the dream there is in 12 years' time or so, we will have the industrial 30% solar panels. Now, to contribute to this global race, at CERES at NUS we have Singapore's National Applied Solar Energy Research, CERES, the Solar Energy Research Institute of Singapore, founded in 2008. We focus on solar cells, PV modules, and solar PV systems. We are about 120 people, including 20 PhD students. We are ISO certified, and we collaborate very closely with companies and the government agencies and society. It's a whole of nation approach to solarize a country and create a solar ecosystem and companies and novel panels. It's quite an undertaking. So the three research areas at CERES with these 120 people are solar cells, PV modules, and solar PV systems. In Singapore, with being an Asian megacity in the tropics with no hinterland, we have to think out of the box where we put these solar panels. So one idea there is, or one approach we do this, is floating solar system. We put solar panels into Singapore's drinking water reservoirs, and there is a 60 megawatt system installed last year. So it's a great success. With the solar cells, one dream that will never stop is by the scientists. They want to squeeze out more electrons out of the square meter. The efficiency, the conversion efficiency of the sunlight must go up. So in addition to these next generation industrial solar cells, which I mentioned, the silicon-based cells, we also talk about these two-junction solar cells, and there we work a lot on perovskite on silicon tandem cells at the moment. And one area with with modules is especially building integrated PV. In Singapore, we have a lot of high-rise buildings. We have more vertical free area than horizontal free area roof space. So we have to really bring solar into the city and bring it onto the vertical facades of buildings. The trend you see at the moment with the mainstream industry, which is this 500 solar football fields, soccer fields per day, is the PERC solar cell here, which has been invented and industrialized in the last 20 years. Now we move to something more microelectronics type, where we improve or minimize the losses, the recombination losses. And so we go to more than 24% efficiency in the factory using very simple processing, mass production, large area. These solar cells are made at a rate of 1 per second in the factory. So ultra high volume production rates, and it has to be dirt cheap. And the next dream then, which many solar scientists have, can't we put two engines into one solar panel and have a tandem solar cell? We bring two materials with very different electronic properties together. One is the well-established silicon at the bottom here, which is a brilliant converter of infrared light, 40% efficiency. But for blue light or green light is not so good, the conversion efficiency for silicon. But for that, we can, for example, try perovskite, a wide bandgap perovskite material, and we learn to process that on the silicon cell, which is actually textured to minimize reflection. And so here we have a strong team, more than 30 people working on this, and our efficiencies is at 26% at the moment. You see that they are using 1 square centimeter device area, and I think we are world leaders with putting perovskite on textured silicon on textured on both sides, which is industry standard actually in the silicon world. The other thing I mentioned, we are in an Asian megacity where lots of buildings, there are also traditional buildings. We must get solar not only onto the rooftops, we must get it onto the vertical facades. And there you suddenly have an additional challenge. You fight with architects. Architects are not engineers. They are more designers. They are more like artists. So we have to come up and make these solar panels in different colors. And this is a real photo in a sense up here. These are some of our solar panels which we develop for building integration on the vertical facades. And we make them in all colors. We make them red, blue, white, black, and even they look like a carpet here. This is a pattern from the historical pattern here in Singapore and Malaysia. So we hope by convincing architects and civil engineers that we can make these solar panels in any shape and in any color that you like. And they are tested, they last 20 years. It's, you know, when you do these things, make them optically more nice, but you have to then be careful that you don't sacrifice the long-term reliability. Again, then in Singapore, where we have little land, we have to look at every square meter that is available in the country, and then we put solar there. So this is we took an airplane and flew over Singapore with laser scanning, and the red areas here are perfect for solar. They are the flat roofs or flat ground areas, and then the vertical facades, you see they are yellow. They only receive about half of the solar radiation compared to the rooftop, and that then of course it becomes an economic challenge to install solar on the facades and make cost-effective electricity. But that's what we do. Every house in Singapore, believe it or not, in our country, has been assessed by us for its solar potential. There is an atlas and it's available on the internet. The other thing, when I say we have to bring solar into the city, we have to put solar onto existing roads, onto flood canals, or use it as PV noise barriers, or existing land that is temporarily vacant, say for construction, but the construction will only happen in 10 years. And the next stream then, okay, if there is no land available on land, then we go onto the water. We have one of the world's largest floating solar systems in Singapore, 60 football fields. And that sits right bang in the drinking water reservoir of Singapore. So that is a great achievement. Solar is benign. You can put it in your drinking water and drink water and get green electrons. And then if the inland water reservoirs are not sufficient, we have to think out of the box and we go out into the open ocean. So this is outside Singapore. The ocean is very calm, and we dream about Solar Plus, where we have 3-level floating platforms where on the top there is solar, we collect rainwater. In the middle level there is vegetable growth. Singapore needs a lot of food and not enough land again. It needs to produce more of its food on its own. And there these floating platforms are great. And in the basement, not visible here, we do fish farming. So it's Solar Plus. You get food, you get drinking water, you get vegetables and green electrons. And instead of using batteries, we would suggest to produce desalinate seawater, use that as a storage for green electrons if you produce too much electricity during daytime. So that's in a nutshell what we do. We try to solarize Singapore and Southeast Asia and develop technologies, solar cell module systems that are tailor-made for Southeast Asia, for the hot tropical climate and urban solar. And so we welcome collaboration here on all these fields. If somebody has an interest or needs some measurements or depositions, we have very industrial equipment, world-class laboratory, so we can help with making, or we are interested in collaborations on PV materials, cells, modules, and systems. For example, somebody mentioned OPV or perovskite. That's an area where we have a strong interest. We have a world record with perovskite on OPV, for example, a tandem cell at 24% efficiency. So we try crazy things in this field, but we also have climate chambers and must make sure the products can survive on the roof for 20 years. And that's it. I hope I didn't use too much time, but I want to give you a big overview about solar. Yeah.
I think that was a wonderful overview of covering a lot of use cases. I'm sure a lot of questions will be there. So I'd now like to move on to Dr. Feng Lee from the School of Physics, University of Sydney. Dr. Feng Lee is currently a lecturer at the School of Physics, and he's going to talk about perovskite halide single crystals for photocatalyst applications. Dr. Feng Lee.
Yeah, thank you for your kind introduction. Now I will show my slides. Okay.
Yes, we can see your slides.
Yeah, okay, thank you. So thanks again for your introduction. So it's my great pleasure to give a presentation here. So my topic is about the single crystal hybrid perovskite for the photocatalyst application. So I come from the School of Physics in the University of Sydney. So from this picture, yeah, you may know that my main research work just on the perovskite materials, which mainly use these materials as an active layer for the phototransistor or photodetectors. And currently, we also try to use these materials as the photocatalyst application. So this is the outline of my talk today. And at the beginning, I will give some brief introduction about hybrid perovskite material and single crystals. And then I will introduce the main work, our attempt on use the single crystal perovskite as the active layer for the photocatalyst, and also the potential area of the collaborations. So I think this picture, Professor Jirish already showed this, and he just focused on the organic materials. So I will talk about the hybrid perovskite. So this one already are treated as the star materials. So from this picture, we can see that the solar cells based on this material develop very fast. Currently, the efficiency is approaching 30%. So it's developed very fast, and it's quite a promising material for the hybrid perovskite. So why this material can be developed so fast in the photovoltaic field? That's because this material has very expert properties, like they have the very long, very large light absorption coefficient, and it's quite easy to tune the band gap of this kind of materials by tuning the concentration of the element, and also quite easy to change the form and the dimension of this kind of materials. And also, this material has very excellent charge transfer property. Based on the different technicals, the mobility is about more than 100, and it's quite depends the different technicals. So in the future, there will be more research on this point, except for the optical property, also focus on the charge transfer properties. And also, this kind of materials has very high diversity. So they have many different forms, and it's quite easy to tune the dimension of this kind of materials. So currently, they already have the 2D layer perovskite material and the 3D and the double perovskite materials. And we can also have different forms of hybrid material, like the single crystal, polycrystals, and also quantum dots, and also nano structured materials. And quite easy to fabricate and grow this kind of materials. We usually use the solution process method to prepare for this kind of materials. So beyond the photovoltaics, this material has also been used for the other kind of optical electronic devices, like the LED laser and some kind of electronic device, like the transistors, or also radiation detectors on the other kind of sensors, like the gas sensor. So except for the nanostructure or polycrystal, single crystals currently attached remarkable attentions, because as compared to the polycrystal, this material have a more promising property. It's also quite easy to fabricate this kind of the single crystal perovskite. We mainly use the solution process method, and also we can use the very easy way to tune the thickness of this kind of materials. We can use the space control, space limited method to reduce the thickness of the single crystal, and we can fabricate the particular device. They have the advanced or more promising property. They have the very good charge transfer property have very higher carry mobility and a very long recombination lifetime. So the carry difference is quite long. So it's quite helpful for design the different optical device and also for the photocatalyst. So except for the remarkable optical and transport property, this material has a very suitable band position. So that would be helpful for fabricating the photocatalyst device, like the water splitting or carbon dioxide reductions. And so far, there are already many publications on using the perovskite materials for the photocatalyst. Mainly, there are three kind of setups, like the vortex integrated with the photoelectron catalysis, and also use the perovskite powder as the active items. And also, they are also use some perovskite material as the active layer for the photoelectrode. So this can be called photoelectrode thin film structure system. So we currently just try to use the single crystal as the active layer for the photoelectrode. So this is the best setup for the photoelectrode thin film structure. And this is the mechanism. So we can just fabricate the single crystal perovskite on the conductive substrate and then put it into the water and some other kind of materials for the particular arms. So this is the best setup for our attempt. So it's quite easy. So this is our first work on using perovskite materials as an active layer for the water splitting. So it's quite easy. We just fabricate the single crystals and use the silver paint to contact the single crystal with the active substrate. So before we fabricate this device, we also check the optical and electrical property of this kind of materials. We found that the mobility is much higher as compared to the polycrystals, and the trip density is also quite low. So that means that the single crystal is not bad from our lab, and we try to use the silver paint to contact this one on the FTU conductive substrate, and then fabricate this kind of device. We also check the performance. So without any protect layer, it can work for 600 seconds without any protect layer. And the performance, the photocurrent just decreased by only 2.6%. So that means that this bulk single crystal have a very good stability. And it can work as the hydrogen productions. The hydrogen production rate is more than 80 nanomole per square centimeter and per hour. So actually, as compared to other kind of photocatalyst, it's not bad, but there's still room for improve the single crystal perovskite photocatalyst. So we currently try to fabricate, use the solution epitaxial growth method, because we want to improve the stability of the device, and also try to fabricate the planet interconnected perovskite single crystal on the FTU substrate. So this one will have the large area, and we hope that we can get the improved device performance. So this is our ongoing project.
Thank you very much, Dr. Feng Lee. That's
Thank you.
quite
Yeah, sorry, I used many times. Thank you.
All right, so
yeah, thanks.
We will take up the questions at the end of the session. Now I would like to invite Professor Bo Zheng to talk about understanding of nanomaterial-based supercapacitors for energy storage. We've talked about generation. Storage is a very important area. Managing interruptions is something that is very, very essential for this transition. So without further ado, Professor Bo Zheng. Yes, we can see your screen. Yes.
Can you see my screen? Okay. It's my great pleasure to attend this conference. My name is Bo Zheng. I'm currently working at the Polytechnic Institute and the State Lab of Clean Energy Utilization of Zhejiang University. Here I would like to share my work, mainly on the understanding of nanomaterial-based supercapacitor energy storage. First, I would like to have a brief introduction of the supercapacitors. The supercapacitor is a type of energy storage device. As you can see here, it looks like the batteries, but it has very different energy storage principle. For the batteries, it's mainly based on the chemical reactions between the electrode and the electrolyte. But the energy storage of supercapacitors is from the electrostatic adsorption. That is, as the electrode is charged, the counter ions will be rapidly absorbed on the surface of the electrode, and it will lead to the energy storage. Since it is a physical electrostatic adsorption process, so the supercapacitor shows a series of unique features. Typically, it can achieve rapid charge with few minutes, even few seconds. So it is much shorter than the few hours of batteries. And also it has a very high power density, which is 10 times higher than that of battery. And it has good reversibility and quite high cycle life. Meanwhile, it is safe and has broad working temperature window. As a consequence, the supercapacitor has been considered as a promising alternative to replace batteries on some application area. As you can see here, the scientists from USA and France published a paper on the Journal of Science to compare the energy storage mechanism of battery and supercapacitors in detail, and discussed the possibility of replacing batteries with supercapacitors in practical high power needed area. Such area is wide and may cover the applications of efficient energy recovery, energy regeneration, and energy supply with high power and high frequency of charge and discharge. For example, it can capture the braking energy of the subways, which experience as many as 1,000 start and stop cycling during a day. And it can recover the potential energy of hoisting load in the port machinery. It can be used on the auxiliary frequency regulation of coal-fired units, and it can provide power for the emergency door operation in the Airbus jet. More and more applications are explored, and the supercapacitor has been considered as an important high-power energy storage technology. The next question is why we need nanomaterials for supercapacitors. So why the activity of carbon is the most popular and the commercial active material for supercapacitors. The carbon-based nanomaterials are quite promising alternative since they have huge specific surface area and high electrical conductivity. It is first demonstrated on 2006. And as you can see here, it is published on the Journal of Science, and it reports the acceptance could be largely increased at the pore size less than 1 nanometers. However, at the same time, it shows quite unique electrostatic adsorption features than the active carbon. Such an abnormal feature has attracted great interest, including not only the ion absorption, but the ion and the water transport. The most important reason is the transport and absorption occur in the nanopores, that is the so-called nano-confined spaces. The pore size is close to the diameter of ions and the water molecules, and thus is cause for a deep understanding of the electrostatic absorption mechanism at the nano-confined spaces. It bridges the unique features and advantages of the advanced nanomaterials and high performance for different applications. So in the past 10 years, my work mainly focused on the science of nanoscale electrostatic absorption. Generally, there are two important effects need to be paid particular attention. The first is the size effect that is due to the nanopores. And the second is the edge effect, which is from the ultra-thin edges of some two-dimensional nanomaterials such as graphene. To review the corresponding electrostatic absorption and energy storage mechanisms, conventional experimental methods probably fail. So in our work, the multi-scale numerical simulation, including the DFT and the molecular dynamic simulations, and also the microscopy measurements can be applied. The first, the following are some results. I will give you a big map, but not the details due to the time limits. The first is the size effect. Using the molecular dynamic simulations, we found that the ion distribution structure in nanomaterial pores shows an obvious size effect, which with the decrease of the pore size, the diffusion layer will disappear, the compact layer will deform, and a single layer structure can be observed. And the mechanism, ion density and acceptance can be obtained when the ion distribution is in the form of single layer structure. So the second is the edge effect. Experimental studies have shown the energy storage acceptance of the graphene edges is much higher than that of the basal plane, that is about 2 to 5 times. This is the so-called edge effect. We want to figure out the underlying mechanism of the edge effect. However, the traditional simulation method probably doesn't work since it is based on the uniform charge distribution assumption. Here we propose a combination of the DFT and the MD. We use the DFT calculation to obtain the charge distribution for the electrons, and we use the MD simulation for the ion distribution. And the results, we can find that the edges and the nanometer confinement near the multi-layer graphenes, it both contributes to the energy storage increase, leading to a 2.5-fold acceptance enhancement. The third is the solvent effect. We try to figure out what is the best solvent for the supercapacitor energy storage. To answer this question, we have carried out molecular dynamic simulation to study the acceptance performance of the electrodes in different organic solvents. So there are some results showing that with changing the solvent, we can change the acceptance. In our work, we also try to understand the ion transport within the nanopores. The self-diffusion coefficient is a fundamental parameter of the electrolyte. It plays a key role in determining the electrolyte conductivity and power performance of the supercapacitors. However, most of the ion diffusion data is limited to the bulk solution, and the pore size larger than 2 nanometers. So we use the MD simulation to get the diffusion coefficients of the ions confined in neutral and charged nanometers, that is less than 2 nanometers. So during the electrostatic process, the ion mass transfer can be divided into 3 forms: the ion exchange, the cation adsorption, and the anion desorption. For the planar electrode or the pore size that is large enough, the ion exchange is the major form. But for the ion electrostatic adsorption confined in nanometer pores, it is still unclear, and I use the EQCM to get some measurements and to get to try to find out the major electrostatic process ion transport formation. Based on the above work, a series of high-performance supercapacitors are developed. So using the vertical graphene bridges, the electron transfer resistance is substantially reduced, demonstrating the supercapacitors with ultra-high rate capability and power density. And a proper combination of electro double-layer capacitance and the pseudo-capacitance shows a great potential to realize both the high energy and both the high power density. So our work achieves their synergetic effect based on some advanced electrode. So in our design, the high active edges and the micro space of the vertical graphene provide more nucleation size for the growth of the pseudo-conceptive materials. As a result, the supercapacitors with high energy density and power density are realized. And the supercapacitors with low working temperature have become highly desirable. However, the energy storage performance declines significantly at low temperature. For example, the capacitance decay of up to a half can be observed with working temperature decrease from 25 to minus 30 Celsius degree. So our work achieves ultra low temperature supercapacitor based on the holy graphene and mixed solvent organic electrolytes. So aiming at the industrial real applications, a sub-millimeter electrode thickness of 100 micrometer is essentially required. However, the thick electrode film suffers from the poor capacity and the power density. So to address this challenge, we proposed a new strategy of interlayer integration energy storage engineering to fabricate three-dimensional porous thick film without obvious agglomeration and stacking. So with this work, we can both high area energy density and power density are achieved for nearly industrial level electrode. So we summarized the above work and published some review papers, not only on the mechanism, but also the development of nanomaterial-based supercapacitors. Meanwhile, the scalable fabrication of high-performance supercapacitors is achieved. And due to the time limitation, I can only have a brief introduction of my work, and more details can be found in our recent papers. And this picture shows an outline of the work that I have a great interest. Okay, the above is my presentation. Thank you for your attention.
Thank you very much, Dr. Bo Zheng. It was a very exhaustive and nice presentation in a new area, emerging area of supercapacitors. Now I'd like to invite upon Mr. Pradeep Murthy to talk about his work on nano catalysts to optimize CO2 conversion. So we talked about generation. We also need to talk about removing the CO2. So Mr. Pradeep Murthy is the Nano Student Ambassador at the University of Sydney, and I would like to ask him to share his research. Mr. Pradeep.
Okay. Thank you very much. Hello, everyone. I'll be discussing my current research progress on my current topic entitled Development and Improvement of Ruthenium-Based Nanocatalysts to Optimize CO2 Conversion. As a brief overview, of course, our climate challenge, such as problems that we face, such as melting ice caps, bushfires, and deforestation, are all consequences of global warming. The biggest culprit, of course, of which would be greenhouse gases, polluting our atmosphere and trapping heat within, and the most abundant of which is carbon dioxide. Over the last 15 years or so, the carbon dioxide concentration has been increasing steadily without any signs of decline, and therefore its conversion or its removal is definitely adamant. The trouble with storing the carbon dioxide is, of course, physical limitations, particularly in the long term, and therefore there are so many issues with storing the carbon dioxide over extended periods of time, and therefore the easiest way to get rid of it in some way is to convert it away. In this particular case, through catalysis. This will not only get rid of the carbon dioxide, or at least convert it away, but also transform it into useful fuels and chemicals that can be utilized in various different forms. The easiest reaction that we could perform this with is CO2 hydrogenation, i.e. reacting carbon dioxide with hydrogen, as it is widely investigated, can efficiently reduce the otherwise inert carbon dioxide emissions, and can generate various valuable fuels and chemicals. In this case, we are researching about the production of carbon monoxide and methane, as they are very simple fuels and chemicals. Methane in particular, very valuable fuel. Carbon monoxide, very good backbone towards generating various other products such as ethanol or methanol, which have very strong fuel potential. The main challenges of such an investigation include how well does the catalyst convert the carbon dioxide? Is it selective to carbon monoxide or methane? And the overall efficiency based on both the temperature and the stability. My research work revolves around developing and modifying the nanocatalyst structure to optimize the carbon dioxide hydrogenation reaction. In particular, we're using the ruthenium active metal as it is highly active and stable for this reaction and is very capable of dissociating hydrogen. The support material is a combination of carbon nanospheres and nitrogen. The nitrogen helps to absorb more carbon dioxide over the carbon surface, and the carbon surface in and of itself can also help to disperse and anchor the ruthenium over it, thereby reducing any deactivation effects, for example, by sintering. Overall, this will create a big hybrid system. This will enable the easier interaction between carbon dioxide and hydrogen with the dispersed ruthenium. Less than 2 weight percent and 2 nanometers ruthenium, as indicated in the literature, will form more carbon monoxide. Higher than this will form more methane. These catalysts were synthesized using a wet impregnation method by loading the ruthenium onto the carbon nanospheres, and that resulted in a mesoporous system, which also based on literature will enable easier diffusion of the gases passing through for the reaction. So my approach to the problem includes asking and trying to answer 3 potential questions. How might different carbon sources for the nanospheres affect the overall catalyst structure? Can an alternate synthesis method, an extension perhaps of the wet impregnation, be more effective towards the overall activity? And overall, how does the nitrogen doping improve the carbon dioxide absorption? So we tested 3 different catalysts. First, to answer the first question, we used resorcinol and 3-aminophenol as the carbon sources. We tested the aminophenol even further by an in situ synthesis method, i.e. rather than directly loading the ruthenium onto the carbon, let's mix them together prior and then form the overall catalyst that way. So it's a much more homogeneous structure. And doping the carbon nanospheres with nitrogen, of course, as I already mentioned. So the key characterization results we have here. So several tests were conducted to determine physical and chemical properties. The first, I'll outline them briefly. We did a BET. This revealed a higher surface area through using the APF carbon source, but using the C2 method generated even smaller pores, which would enable easier diffusion of the gases within the structure and therefore more reactivity. An XRD revealed smaller peaks in the C2 catalyst, which would indicate more ruthenium dispersion, and according to the literature as well, would generate more carbon monoxide at elevated temperatures. The TEM results reveal that the C2 catalyst had the smallest average ruthenium particle size and was the least dispersed, thereby removing any signs of major agglomeration when these catalysts are inevitably subjected to high temperature reaction tests. And also, by the way, the shading indicates that some of the catalysts might have been, or definitely were, immersed within the porous structure. And finally, XPS, which indicated more carbon-nitrogen interactions, which would help both to anchor the ruthenium onto the surface and also enable more carbon dioxide absorption over the catalyst surface. And that way we can get a more hybrid system between the ruthenium and the carbon-nitrogen, which can enable more reactivity from easier H2 dissociation and CO2 absorption. Okay, so the key activity results. So we tested the catalyst from 350 to 700 degrees Celsius. The C2 catalyst, as marked in red, indicated an increased activity or increased CO2 conversion beyond 600 degrees, whereas the other two declined in activity because of this agglomeration effect. The carbon monoxide selectivity increased as expected, while methane decreased because this reaction would be endothermic at higher temperatures. But there were also, rather intriguingly, we managed to find an increase in methane selectivity up till 500 degrees Celsius. Because there was some ruthenium discovered within the porous structure, this would have contributed towards more hydrogen being dissociated within the pores, and increased contact between carbon dioxide and hydrogen would have enabled more methane to be formed instead of carbon monoxide, and therefore that is the reason. And subsequently, obviously, methane decreased beyond, because then the reaction becomes less significant as the temperature is increased from being exothermic. And then subsequently we did a selective stability test, whereupon the catalytic activity, CO2 conversion remained perfectly stable at over 10 hours, whereas the other two catalysts declined in activity, thereby making it much more active. By the way, we did this test at 600 degrees Celsius, and the C2 catalyst was the most active. To further confirm why this was the most active, by conducting a TEM analysis post-stability, we can see that the catalyst remained quite, the ruthenium catalyst remained quite dispersed. What?
Mr. Pradeep, maybe about a minute, because I think we are running into the next session.
Yeah, I'll finish very soon. So there was high dispersion of the ruthenium active metal as compared to the other two catalysts, which showed very high signs of agglomeration. So to summarize all of our findings, the C2 catalyst remains the most promising from high activity and stability with high dispersion of small ruthenium nanoparticles, displaying a high affinity for CO2 conversion and selectivity, either to CO or CH4 according to which temperature we're operating at, especially with the inclusion of nitrogen doping to increase that absorption capacity, and the in situ method improving the dispersion and ruthenium depositing within the mesoporous structure. So the major research impact, this catalyst has shown very strong capabilities of addressing the current climate challenge, from reaching high CO2 conversion levels into desirable fuels and chemicals. It would have a strong applicability in industry, especially if using only 1 weight percent ruthenium, as ruthenium is expensive. So if you use less, it could be more economically feasible if sufficiently active. And of course, encourages further research into carbon conversion systems in terms of understanding how different carbon sources might affect the overall structure and correspondingly the activity, the interactions between the different materials towards contributing towards this major hybrid structure and the corresponding mechanism. And of course, the strong metal support interaction towards improving both CO2 absorption and subsequent activation. Thank you very much.
Thank you very much, Mr. Pradeep. So with that, we come to a conclusion of a very interesting and active session. So now we'll move on to the a brief discussion on question answers. I don't think we have much time. Maybe we have time for one question. So I would like to pose this to Professor Armin, where there were a lot of technologies that was spoken today about carbon conversion, new solar cells, and a lot of initiatives, but all of this comes with a cost, the cost of renewable energy, be it solar or wind or any of that pathway. So Professor Armin, based on your experience working in deployment of solar research initiatives, how do you think these are likely to evolve or emerge? What kind of activities or what kind of supporting infrastructure or policies need to be there for these pathways to mature?
It was also a question by one of the students who attended. Solar and wind are expensive, and I must say I totally object. Right today, if you are in Saudi Arabia or UAE with large desert climate, no clouds, cheap land, then solar there are auctions, big gigawatt power plants, and there they sell electricity for $1 to $2. So solar today already is the cheapest electricity on the planet, if you have a very sunny climate where you probably don't want to live. In India, it's probably $2. In Singapore, it's probably 3 or 4. So if people think solar is expensive, they are completely wrong. They did not appreciate what happened technology-wise in the last 10 years. And the same with wind. And now with fossil fuels and climate change, we have to electrify everything globally. And we have to go, decentralized power generation, power to the people. Have we put it on rooftops, on every empty square meter, wherever you are, land, roads, canals, oceans, if you wish, or water reservoirs. And I'm personally 100% convinced that in 2050, most countries on the planet will be powered by renewables, mostly solar and wind. And we have to solve the problem that there is intermittency. We are weather dependent, right? But Mother Nature is also weather dependent and has wonderful trees and plants. We have to learn that that's where energy storage comes into play, either batteries. The much cheaper thing, if you live in a hilly country like China or India, you do pumped hydro. I don't have time to explain, but pumped hydro is 100 times cheaper than battery stored electricity, and many, many sites in the world, hundreds of thousands of sites. We will go to 100% renewables within 30 years. It's unstoppable. And the question is only which countries will be leaders and who will be laggards and who will be also both as a user and as a technology leader, right? In all these countries here, India, China, Australia, and Singapore, they're all different and have unique and great opportunities for making the switch to a sustainable energy system.
Absolutely. I think you're bang on the point. Solar in India is now cheaper than coal, and
exactly.
I think
we
that's
hear it all the time that it's too expensive. I don't know why people don't understand.
I think you are absolutely. It's the tides have completely changed, and I think solar is almost mainstream. So now this next question is to Professor Girish. Talked about a wonderful system on using organic cells and cavity-based pumping up of light. Now, what do you think it takes for these kind of technologies to win? So there are so many alternatives that are emerging. Perovskites are there, and there are many things. And previously also we have seen SIGs and other dye-sensitized solar cells and all, but silicon is still the mainstream. So what do you think needs to fall or needs to happen for some of these new technologies to win?
I mean, it's virtually hard to beat silicon. So the thing which we have looked into with interest is the beauty about organics, which I find, is that you can tap a larger part of the solar spectrum, which you typically can't with silicon. So one of the things which some of the groups in Australia have been focusing on, how to kind of use phenomena such as Singlet Fission, which is where you kind of tap basically UV radiations and can split the photon into 2 triplets, which are which match energy of the silicon. And then the idea is that you can harvest that UV, create 2 triplets, which can then feed into silicon. And then there is whole work going around up conversion, where you actually harvest near infrared photons or excitons and basically fuse them to get essentially energy match with around 1.1 EV or so. So basically the way to kind of tap an entire part of solar spectrum using organic molecules is then to essentially feed energy into devices which have proven to be working already pretty good. So there is a push going towards understanding how we can merge these organics to tap larger part of the solar spectrum and feed it into tandem devices, which basically Armin did talk about, that we are going towards tandem, which is essentially not only perovskite silicon but organics silicon as well. But there the major issue is organic inorganic interface, which is where a lot of research has been going on. So I see that's where essentially organics can make substantial contribution, not by themselves as much.
Thank you very much. I think I've got the indication on time limit. So wonderful having you all as panelists here. It was a great session, and I hope that we can continue the discussion going forward through whatever means. A pleasure to meet you all. And with this, I conclude the session, and thank you very much once again.
Okay, bye-bye.
Thank you.
Hello, Professor Xiao. Let's start the session 4. Thank you. 没有开声音. Please unmute yourself. 没有开声音.
Oh,
yeah, I think you're still muted.
okay. All right. Well, welcome to this session. Thank you for attending this session, and it's first time to meet all your gentlemen and ladies and gentlemen. And I have been charged to be the host to chair this session. So our session is on sustainable city and construction. And because of the time limit, I'll just start to call the speakers first. Our first speaker, based on the order, is Professor DiMartino, Christopher DiMartino. Christopher, well, I will not read on the bios for these speakers. I'll just quickly to read a few things. Dr. DiMartino is currently an assistant professor and a research fellow at the Zhejiang University UIUC Joint Institute. His specialty is in structural engineering, but with a lot of focus on sustainability and many other issues. He uses a multidisciplinary approach to many of the outstanding problems in the sustainability issues. Dr. DiMartino received his degree from University of Reggio Calabria and Sapienza University, Rome. Now, Christopher, please start your presentation.
Thank you for the introduction, and thank you to the organizer for this opportunity to share with you some ideas. As you know, I will have only 10 minutes, but I will try my best to summarize our research achievements. I hope you can see my screen. If you cannot, please let me know. The title of my presentation is JGUI Research on Infrastructure Resilience for Cities with Livable Environment. My name is Cristoforo DiMartino. I will try in this short time to give an introduction of what we are doing. As you can see, the first two photos you can see in this slide are basically the two cities I will describe in a while. On the left, you can see Hangzhou in Zhejiang province, where the province where our university, Zhejiang University, is located. And you can see the city of Chicago in Illinois, where our partner university, UIUC, is located. Okay, I would like to give you some background. I mean, mainly during these days, during the last 2 days, we had the opportunity to learn a lot about the problem of carbon neutrality. But there are several problems we are facing nowadays. One of the first problem is the growing of the population worldwide. You can see this figure on the left showing that the population is growing. So this means we are much more people. The improvement of the technology is making people to move to urban areas. So we have a very high increase, especially you can see in the last century, of people moving from rural places to the cities or to urban areas. And this is basically producing an increase of the population, needs for more space. You can see this picture in the middle showing Hong Kong, some incredible, concentration of people in a small area. But you can understand very well that when you live in a city, you need resources. And these resources are needed. And as you know, we are living on this planet. This planet is our big home, but I mean, it's unlimited in terms of quantity. On the other hand, I mean, the improvement of the technology certainly led us to have an improvement of the quality of life. I like to share with these photos of Shanghai. This is a photo of Shanghai, of Nanjing Road, one of the most important streets in the city center of Shanghai at the beginning of the last century. And if you have been recently in China, you know very well Nanjing Road nowadays is one of the most important economical center in the world. But you can understand that the transition from this first picture to the second picture is not free. And everywhere in the world, we observed an increase of the carbon oxide emission. And as we know, I mean, I will not summarize the problems, but I mean, there are several problems related to the carbon oxide emissions. Certainly, more developing country like China had a huge impact, but recently you can see there is a correction of the trend thanks to the new policies. And also in the developed country, this trend is continuing to increase, but with some general reduction. But in general, we are not doing enough. Another problem we are experiencing in our cities is the increase of the global disaster. So you can see here that the global disaster has continued to produce the losses. This is a figure representing the global disaster in terms of GDP, basically in the last around 30 years. And you can see that still we are losing a lot of money on disasters. And all this effect, I mean, there is a big debate in the literature on how much the humans are influencing this, is producing the climate change. The climate change is the change of the behavior of our system with an increase of the highest or the peak value. So you can see we record extreme weather. According to this, between Zhejiang University and UIUC, we decided to start a new research center. In reality, is part of a research center because there are 3 joint research centers to rethink the city. So this is Hangzhou again. This is the way we know our cities nowadays, but we really feel as people in academia that we have to think a little bit more about the new cities. So we founded this Circle. Circle is a center for infrastructural resilience in cities as a livable environments. And you can see the center is between Zhejiang University in the US and Zhejiang University in China and the University of Illinois in US. And you can see that that's our logo, and you can find a lot of information about our activities on this website. The center we founded is multidisciplinary by definition. So you can see here, it's led by Professor Shao, with the chair today of our session, Professor Bill Spencer from UIUC. And we are divided in 4 main areas. You can see water, environment, and trust, energy trust, build infrastructure, and transportation. With the idea, you can see, of rethinking the city in a trust integration infrastructure and improve the life of people and thinking about their livability. We are working on different research directions. In particular, you can see here data analytics. All the possible technologies that we can adopt to reduce the carbon emissions, machine learning in order to better understand using data-driven approach how a city is working and how we can improve the quality of a city. And the final goal is certainly to provide a city with larger resilience, so capable to resist to the stressors we have every day, and at the center, the humans, with the idea to have the livability and the humans at the center of our actions. So our general research efforts are generalized to create a cyber model of a city. The idea is to have this cyber model containing the infrastructure system, containing all the new technology we can adopt, the sensors and so on. And in particular, that's our mission, to take care of livability or put humans at the center of our action. And in general, you can see we are using physics-based and data-driven modeling to construct this regional cyber model, able to provide short-term predictions and incorporate all the possible variables, and at the end of the day, improve our system considering the variables I just told you. Our research directions is very wide, so we are working in the digital twins of infrastructure. You can see here, we are working as well on prediction at regional scale of climatic variables, also prediction of the weather conditions, or let's say the climate change at world level. At small scale, we're working also on bio-based material. You can see this is a building just realized in China using new bamboo technology, and also autonomous driving. You can see this is one of our students in our campus experiencing and trying to use this autonomous driving. We are looking for several cooperation areas, in particular in qualitative analysis. As I told you, humans at the center of our action, so sociology, psychology, and healthcare. The idea of new materials, so nanofabrication and smart materials. And also, since we want to develop cyber system, machine learning, robot, and sensor and actuator. And as you can see here, the final idea is clearly to build a worldwide cooperation on this topic. We are also trying our best to opening a discussion platform and to learn more from the most important player in the area. And we are organizing this series of Circle Distinguished Lecture. I would like to advertise with you. You can see the previous lecture on the left side. The last lecture will be a few days later with Professor Jingguan Tang, who is the president of PolyU in Hong Kong. I mean, you are all welcome, and we look forward to have more cooperation in the near future. Thank you for your time. I hope I respected my 10 minutes strictly.
Well, thank you, Dr. DiMartino. Thank you for keeping the time, and your time is very well controlled. Considering we don't really have too much of a time, so we're just continue our presentations and maybe leave some of the question and answer area time to the end. And also we have concluding session slot. So our next presentation would be given by Professor Manu Sensamnam. And sorry if I pronounce your name incorrectly. Professor Sensamnam is a professor in the Department of Civil Engineering, IIT Madras. He has a very wide areas and obtained IIT degrees and also from degrees from Purdue. Considering the time, I'll just pick a few maybe the very last one. Professor Sensamnam is also
Professor Manu, you may go forward. I think he's
okay. Sure.
Yeah.
Okay, I'll share my screen and start immediately. I hope you can see my screen.
Yes.
Okay, thank you. So, yeah, thank you very much for this invitation to participate in this very interesting seminar. I'm from my side, I'd like to bring to you some technologies for lowering CO2 emission in concrete construction. Several of these aspects are being worked on currently at IIT Madras, but in general, I've also tried to put together some things that are in the interest of pursuing globally as a whole. So, concrete is definitely a very vilified material with respect to its impacts in terms of CO2 and energy. What we know that nearly 8% of CO2 emissions are from cement manufacture, and generally about 20% of the CO2 emissions are attributed to the building industry overall. But what happens is if you really take a complete look at concrete, the embodied energy and the CO2 emissions that are coming out from concrete are much lower than for other building materials, including wood, glass, and steel. So that's quite a surprise to many. But if you really do the math right, that's what it comes down to. The only difficulty is that we're using concrete in very large quantities. If you look at the estimates today, it's about 25 gigatons. So it's the largest ever used material, of course, second only to water. And that causes the impact of concrete to be very large. What we also have to put in perspective is that the majority of the CO2 emissions from concrete are attributed to cement. So the less cement there is in concrete, the better. So that's one way forward already as to how we can reduce the impact of concrete. Now, what are the various ways in which we can lower the impact of concrete? One aspect that we have to realize is that we cannot reduce the use of concrete in many geographical locations wherever development is still happening, especially Asian countries and African countries. There's a lot of concrete that needs to be used. The average consumption of concrete in these countries is much lower than that of the Western countries. So definitely there is potential for increased use of concrete in these locations. So what we can do, while we cannot reduce the amount of concrete, is we can definitely reduce the cement that is used in concrete. What you can do to reduce the cement is by using supplementary cementitious materials. Typically, these are byproducts from other industries, and they possess properties that are complementary to what you have with Portland cement and concrete. Very often, the shift to a performance-related specification for construction projects can help us actually save quite a bit of cement and reduce the environmental footprint of concrete to a large extent. Today, many of the standards across the world follow a prescription-based approach, and that's really not very helpful with respect to bringing in innovation with respect to construction. The other aspect is to maximize the amount of aggregate that you can use in concrete. I know that there are possibly not too many takers for this approach, but if we start looking at other industries, manufacturing industry, powder metallurgy industry, and so on, there are a lot of concepts that can be actually applied in the design of concrete in such a way that we can bring down the amount of cement that is required to produce the concrete. There are a lot of research studies today on looking at alternative cements. Some special cements are also derived which are carbon neutral, as a result of which you can bring down the overall impact of the concrete itself. And there are low carbon cements. They are not carbon neutral, but certainly much lower carbon dioxide emitting cements as compared to your regular Portland cement. One thing that we cannot turn our eyes away from is the use of recycled concrete and industrial waste for aggregate, because aggregate, or the part that is likely to be inert inside the concrete, that's contributing nearly 75% of the volume of the concrete. So most of the concrete is basically aggregate. So if you start utilizing industrial waste and recycled sources, you can reduce the impact on natural sources. Carbon dioxide curing or CO2 sequestration within concrete is an option that has been suggested. There are limitations with respect to the chemistry, but then there are strategies which can enhance this also by capturing the amount of CO2 inside concrete and utilizing carbon dioxide for actually curing the concrete instead of water. The other possibility is looking at repurposing concrete. Rather than trying to crush concrete and reuse it again, we repurpose the material by a suitable architectural and engineering related design. So this is something that we need to look at in the future in the long run. I'll just touch upon a couple of these in a little bit more detail. We know that supplementary cementing materials are a really useful solution to reduce the impact of cement and concrete. But what we also have to realize is that geographically, not many of these are available in large quantities. One thing that you have available in large quantities is clay, and which can be calcined to obtain a significant degree of reactivity, and that can help reduce the quantity of cement and concrete. The other industrial byproducts like fly ash or slag oftentimes are either very limited in their quantity, or sometimes in the case of fly ash, it may be present in large quantities but unusable because of the high degree of variability and poor quality that is associated with much of the fly ash. Volcanic ash and other forms of naturally occurring materials, supplementary materials, one cannot do a real estimation of to really understand how much of this can be available for substitution for cement. So the realistic possibility today is to utilize possibly the vast reserves of clay that are available. And these are not pure clays. These are highly impure clays which are lying as overburden in many of the China clay mines. And these can be combined with limestone that is available in cement mines, which is not really being used for cement manufacture because of being of a poorer quality. And there's a lot of emphasis today on the use of this combination of limestone and calcined clay as a possible replacement of cement. Now, of course, when you're starting to go from your cement towards other types of binders, you have to realize that the chemistry has to rely on this reactivity, which we call as Porcelainic Reactivity, where the alternative materials start reacting with the lime that is available in the cement. So there is some degree of availability of lime that basically dictates the amount of reaction that can actually take place. So we are looking primarily at the Porcelainic type of binders, which can enhance the quality of cement in the long run. Now, the other route, of course, is to start looking at an alternative chemistry rather than utilizing Portland cement for the reactivity of these aluminosilicate materials that are abundantly available. We start utilizing alkalis to activate these materials. So alkali activated composites, or geopolymers sometimes as we know them, can be quite a useful option. Only problem is, of course, handling the alkaline solutions like sodium or potassium silicate and sodium potassium hydroxide to activate the aluminosilicates that can be quite hazardous to do in a regular construction environment. So it has to be done very carefully. So what it essentially does is it dissolves the aluminosilicate and recrystallizes it in a form that leads to hardening and strength development. So alkali activated composites could be a potential solution for reducing the impact of cement in concrete. There are other special cements, as I talked about earlier, calcium sulfoaluminate belite cements. These are quite popular in some parts of the world, including China. So here, the idea is that you're producing cement at much lower temperatures than ordinary Portland cement. So you're essentially contributing to lesser amount of CO2 that actually goes into the cement itself. There are magnesium-based cements that have been promised to have a lot of potential for replacing your regular Portland cements. The problem there is, again, the abundant availability of magnesium-based materials, which is quite low as compared to the calcium or silicon-based materials. There are cements that are actually formulated based on CO2 curing, carbon dioxide curing. One of these is called Solidia. It's a wollastonite-based cement. And the idea is that while when you mix it with water, you cure it in a carbon dioxide environment, the CO2 is basically captured and you convert the active phases into calcium carbonate and calcium silicate, and that leads to a sequestration of CO2 in your systems. Again, the chemistry can only dictate that you can sequester only a part of the CO2, not a large amount in this case, but still there are modifications being made to several chemistries to try and fit in a lot more CO2 into the cementitious systems. Now, the question that we need to ask is there a future without regular cement? Of course, being a cement and concrete technologist myself, I would rather believe that no. But then there are obvious reasons why I want to state that there are very few alternatives. I gave you some of these alternatives, but not many of them have a long-term potential, because in cement, we are already utilizing a lot of the materials or minerals available in the Earth's crust in an optimal fashion to produce what we call today as Portland cement. What we have to do, of course, is move forward to restrict the use of cement and concrete by bringing in more supplementary materials and adopting these alternative cements judiciously, and also moving towards performance-based specifications. The other aspect I'd like to touch upon briefly is that we have alternative sources for aggregates that can be used in concrete. As I said earlier, aggregates constitute a large volume of the concrete and can really have a major impact on the CO2 that is associated with concrete and building construction industry in general. We can look at manufactured sources. That means industrial byproducts like granulated iron slag aggregate, air-cooled iron slag aggregate, steel slag aggregate, and copper slag aggregate. Again, there are difficulties in completely utilizing these materials because they possess some properties which are deleterious to the long-term performance of concrete, but one needs to have some degree of processing done to get these to be suitable for concrete. Construction and demolition waste today is an absolute necessity to look at. One has to build in policy that can actually make mandatory the use of C&D waste in concrete. But then again, we need to have a proper source segregation to ensure that we are able to control what actually gets into concrete. This could be recycled aggregate, which is a mixed demolition waste, in which case you have to be very careful about utilizing it for structural applications. But you can definitely go for recycled concrete aggregate, where you are actually crushing old concrete into aggregate to be used in new concrete. So again, there are technical issues that need to be sorted out there, but in most cases, it is possible to actually utilize a large fraction of the aggregate as your C&D waste. The questions that we need to ask is, do we have enough of these materials? Is there a good spread? Because we are talking about huge quantities, right? We are talking about very large quantities to make the kind of concrete that we want. We need to have some degree of processing done to remove unwanted material and only get the useful fractions inside the concrete. But that may still involve some CO2 and energy emissions. Energy demand can sometimes be high. One has to look at the long-term stability of these materials also to some extent. Processing methods have to have some degree of understanding, because you need to bring down the amount of CO2 and energy contributed by the processing method itself. And what we need to do is probably readjust our sustainability framework to take into account some policy decisions which prevent the use of natural materials, and also take into account the indirect costs of actually dumping all this recycled concrete in landfills. Because again, if it has a cost associated with it, we'll be more prone to using such materials inside the concrete. So I'd like to thank all of you. I just wanted to put together some ideas as to how we can lower CO2 footprint of concrete. I'm definitely available for interaction, but you can also email me in case you have any questions on this subject. Many of these things are active research ideas that we are pursuing at IIT Madras, and I'd be happy to engage in any discussions on this subject with you. Thank you all very much.
Well, thank you very much, Professor Sen Lam. Our next presentation will be given by Professor Heng Chi Kiang. Professor Kiang is currently a director of the Center of Sustainable Asia Cities, and he has also served as deans and the department chairs at NUS, and also visiting professors at the various prestigious universities, including the Tongji University in Shanghai. Now, Professor Qian.
Thank you. Let me try to share screen. Can you see my screen?
Yeah, it's visible, but you can share in the full
yes.
screen. Yeah,
great.
It's fine.
Please go ahead.
So I will, well, my topic is really sustainable cities by design, where I look at architecture, urban design, and planning. And as I said, you know, we are confronted with all sorts of challenges, and you can see them in very faint in the background. And that architecture, urban design, and planning really matters in the making of sustainable cities. And in this image that I did in 2008, I basically say that sustainable development can be achieved only through ingenious design. And design includes the whole range of architecture, urban design, planning, etc. And appropriate applications of new, if necessary, technologies and responsible behavior. So that's the triangle that is absolutely important if we want to achieve sustainability. And at different scales, be it from the building, the site, neighborhood, city, region, national scale, at different scales, the kind of problems are different and the solutions are also different. So let us start with this particular solution that was applied in Singapore. In 2008, we converted what you see here on the top left-hand corner, a concrete canal that conveys water from point A to point B in the fastest manner possible. We converted it in a span of 3-4 years into this stream at the bottom here, which can, because of the terrain, the shape of the terrain, molded to expand into a significant river when flooded. And in so doing, it not only conveys water, it retains water, it recharges the aquifer, it promotes biodiversity, it reduces temperature, etc., etc. So it becomes immediately an environmental and also social, recreational, economic, and aesthetic asset. So that is the power of design. It is instead of a engineering solution, as we can see in 2008, which is basically a one-shot, one-kill kind of solution. Planning and design are multiple objectives solution generators. So I'll quickly look at the range of research that we have done over the years. I'll select a few to show at the different scales, S for small, all the way to XL for extra large. You can see that at the building scale, for instance, we have applied this to our own building, a building we built a few years ago, as a zero energy building, we call it SDE4. SDE4 in NUS, it is a building. It's a zero energy building, and it not only zero energy socially, it's also a very successful space, and it also harvests rainwater and phytoremediation for the recycling of water. So we, in our endeavor to generate this design, we used all kinds of, we basically maximized our, we call it passive strategies, passive design strategies, but even then, of course, we cannot achieve zero energy because of our air conditioning system. Aircon, as we know, is the biggest guzzler of energy. And finally, we adopted a hybrid system whereby air is pumped in at a elevated, more elevated temperature between 26 and 27 degrees, but supplemented by ceiling fans, smart fans. And after several iterations from design to technology, we finally managed to reduce our energy consumption and made the PV production via 1,200 over PV panels on the roof to cover whatever energy needed. So that was at the building scale. At the urban design scale, which is M, medium scale, there are yet other solutions that we can help to optimize our design. So, and it doesn't prevent us from applying what we learned in the earlier smaller scale of building and apply them in the building that are in this building clusters. By the cluster level, we have done research, for example, in this case, sustainable housing typologies. And in this particular research, we selected close to 100 typologies of different sorts with different densities and plot ratios, or FAR, of different intensities, and looked at a number of key environmental variables such as sky exposure, daylight, solar radiation, wind and noise, and all these have implications on physiological comfort, be it thermal, visual, acoustics, or psychological well-being, but also on energy consumption and urban heat island effect. And it also, for example, in the case of wind, influence impact on the air pollution dispersion. So again, through our modeling, and I won't go into the details here, modeling for all those particular environmental variables, we're able to come out with, you can see here, actually there are about 92 points in here, and with the Pareto ranking here for multidimensional optimization, we can see that for different, even for example, at a gross floor area of about 3.4 along this line, you can see that there are typologies that perform really quite badly, and typologies that perform pretty well. So all this to say that, and you can see some of them perform all the way up there. So all this to say that design really matters. Design and typologies matters in the case of performance. So as you can see, this is how we do it. We subject our typologies to simulation, and from whatever I've learned in this clusters, we apply the principles to the redesign of this particular cluster here, and in the different proposals, we're able to then ascertain which is more environmentally friendly. Another kind of research that we do is, for example, how do we use planning and design to mitigate the impact of storm surge? So one of our studies is, in fact, to see how do we, in planning the waterfront with simply the array of different arrays of buildings, reduce the impact of storm surge. So this is a PhD dissertation done by a student of mine, who's now currently teaching in Salmon University. And you can see all the simulations done, and to the different array of these buildings, tighter or denser, and the different orientations, we can, through design and planning, mitigate the impact of storm surge. And again, through this principles learned, it was applied again to another site in Marina South to test the validity of the solutions. So this is these are two different designs and kind of impact created by storm surge. Finally, at the much larger scale, for instance, at the island scale, we could see that planning now becomes very important. How do we, for example, in this particular area here, pardon, this three oval should really be shifted 2 cms up to cover this areas, and this area here. We can see that in Singapore, the eastern and middle part of Singapore, western and middle part of Singapore are cooler than this eastern part. So how do we, through the planning of Singapore, lower the temperature in this part of the island? So it so happens that we have an air base here, an air base. You can see the air base in this location here, that is due for moving out. So in about 10 years' time. So with that comes the opportunity to entirely replan this area. And one of our research then looks at the wind corridors, the wind corridors that are currently there, and we model all this, and the green connections that could be extended to connect to the central catchment as well as the western catchment, and in so doing, with our planning solution, it could reduce the temperature of this western side rather significantly. I think this is the last slide I'm going to show, part of the planning solution that my colleagues and I work with our students to achieve. So with that, thank you very much, and I'll be happy to take any questions later if you have.
Thank you, Professor Kiang, and we will have the question and answer time at the end of the presentations. Now I'd like to move on to the next presentation by Professor Lee Prost. Sorry if I pronounced your name incorrectly. She is currently at the School of Civil Engineering, University of Sydney, and she's serving as the Deputy Director of a Sydney Manufacturing Hub. And she has a very broad area experiences with a degree from material science, I believe, and also her experiences include the research and the studies both in US, France, and elsewhere, and certainly in Australia. Now, Professor Prost.
Thank you for the introduction. Do you see my slides properly?
Yes, very well.
Okay, thank you. My name is Gwenaëlle Proust. I'm a professor in the School of Civil Engineering, but I'm also the Deputy Director of the Sydney Manufacturing Hub, and I'm going to show you a bit of what we do and what can be done in terms of advanced manufacturing in the city of the future. First, like if we talk about advanced manufacturing, we're talking about using innovative technology and methodologies for improved competitiveness in the manufacturing sector. So how can we translate that in the construction sector? What is the relation with advanced manufacturing and the city of the future? So there is different way this can be looked at. So first, if we talk about technologies, additive manufacturing, also called 3D printing, is an area that a lot of progress has been made in the recent years. And there will be, for sure, and there is already applications that are related to civil engineering for construction or structural engineering. So I'm sure all of you have heard already about 3D printing of concrete. And I put an example of that on the left side. And there is different videos that you can find online now showing how they construct house using additive manufacturing of concrete using robotics as well. Another area that I'm illustrating here is also 3D printing, but this time it's looking at metal. And in this case, we're looking at connections in steel structures. So the freedom of manufacturing complex shapes, and also the fact that joining techniques to create those complex components are not necessary, make that 3D printing can be a great advantage in this type of area. So here's an illustration of a research done by other people than myself, but illustrating like 3D printed metallic connection for steel structure. Another area of advanced manufacturing that I think will have a large role to play in building the city of the future is robotics. And here again, I've illustrated that with some examples. So on the left side, you can see robots are being used to place concrete on some composite steel concrete structure. And showing that, so in red, you can even see like the path that they're going to follow. Another area where robotic will be of interest is for welding, especially for complex welding or repetitive welding, sorry, I should say, where now robotics can be used. And the advantage is that you also be able to maybe reach areas that will be difficult to be reached by the human, so removing the risk associated with the aspect of their job. So now, if I want to look at a concrete example of what I do, so here is an example of upcycling wood products in wood plastic composite, and we're going to look here at some application in facade engineering. John, Jordan, and Yerong are my past and present PhD students who have worked on this project. And Sandra Loshka is my collaborator at the University of Sydney who works in architecture. So the objective of this project is first develop a sustainable wood plastic composite filament that we're going to use to do 3D printing. So in which way is this wood plastic composite is going to be sustainable is that we're looking at recycling polymers, but also wood chips, for example, that are produced from the industry of timber. So, and the idea is that we should be able also to recycle the facade panel, for example, once it's used has been terminated by remelting and reproducing filament. We also want to look at, can we create something that looks like timber? We just don't want to just have a brown color facade, but have the aesthetic of wood. And then make sure that we can have some applications where we have some structural property, as well as some water absorption property, limit that will increase the lifetime of the facade. So as I say, we're looking from a point of view of material to create our own material to print. So we are making wood plastic composite using extruder to make filament that we then use in the technique of fused filament fabrication that everybody is now aware of, where we melt this filament and deposit layer by layer to create a 3D component. So if I want to first look at the wood aesthetics, so this is an example of a panel that we have created on the lab, which is 400 mil by 400 mil. And by playing with the technology, with the software that control the motion and the temperature of the nozzle of the printer, we can make in so that we don't have a uniform structure at the surface, but we have something that can be reminding us of the wood grain of the material. So this was our first attempt at doing aesthetics. So this only a surface. This is only not a 3D representation at the moment. And then we want to look more at 3D surface and being able to also produce complex shape while keeping the aesthetic of wood, but not have necessarily flat surface. So once again, this is done by using wood plastic filament. And then by changing the parameter of the printer, we are able to create, you see those shapes which show like a wavy form at the surface. So this will give us quite a lot of opportunities to develop some aesthetic for facade engineering using such material. Now, if I put my other hat on and talk about the capability we have in the Sydney Manufacturing Hub, because there is a lot of other things we can do. So this is only one example of one of my projects. But at the Sydney Manufacturing Hub, we want to have the capability to manufacture 3D manufacture using additive manufacturing, a range of material, metals, ceramics, polymer, composites. We already have a range of technology available for 3D printing. And we also have a range of equipment available for the design of the components and the optimization of the process, as well as post-processing of the equipment, post-processing of the component to improve properties after the manufacturing process. And to finish my presentation, I'm just going to leave you with a short presentation. It's only a minute, and of the Sydney manufacturing. And just here are the contact information if you want to, sorry, just the website if you want to find some information about what we do and if you want to contact us. Thank you.
Thank you very much, Professor Prod, and I see a lot of interest that we can collaborate. Thank you very much. Let's move on to our next speaker, and in this session, this is the only presentation by a PhD student from student side. The presentation will be given by Ms. Shu Siqi, and her presentation is greener and more sustainable future for a rod-free transportation. And she is currently a PhD student at the Zhejiang University UIUC Joint Institute. I think she got her bachelor's and degrees, master degrees from Imperial College, London. Now, Siqi, please.
Thank you. I wonder whether you can see my slides or not.
Yes. Very well.
All right. Okay. Thank you. Thank you, Mr. Xiao. My name is Siqi Shu, a PhD candidate from Zhejiang University, University of Illinois at Urbana-Champaign, and I'm from the Transport Systems and Environment Lab, supervised by Dr. Simon Hu. So I think everyone who is on this webinar, we've all got the same objective. We all want to deliver a carbon neutrality outcome, so in all sets of sectors. And today I'm going to be discussing about green and sustainable road-free transport, which plays a significant role in carbon neutrality. So first, in the worldwide big picture of carbon reduction, clear goals are set. For example, the Paris Agreement sets long-term goals to guide all nations to limit the global temperature increase in this century to 2 degrees Celsius. And in accordance with this goal, in China, plans and agenda are made to achieve the carbon peak goal by 2030 and carbon neutrality goal by 2060. Road transport itself is at the same time a major source of pollutant emissions with both environmental and human health consequences, and a primary system supporting the expansion of trade and consequently economic activities. Therefore, transforming road-free transport into an environmentally and socially sustainable system is critical to improve the well-being of current and future generations. In terms of the CO2 emissions, road freight is one of the fastest growing CO2 emitter. Let me introduce some basic background numbers. As you see here, road freight consumes around 50% of all diesel fuel and accounts for about 80% of the global net increase in diesel use since 2000. Projections see road freight activities at least doubling by 2050, offsetting any expected efficiency gains and lead to an increase in emissions by 2050, not a reduction. Given that global carbon reduction goals have already been set, efforts are made globally. Evidence and best practice for decarbonizing transport, such as changes of logistics operations, use of alternative fuels, and applications of intelligent transport management strategies, are studied and shared globally. So as a researcher, what can we do now, and which approaches to follow to aid the decision-making on policies and strategies for achieving the goal mentioned before? And here, a pathway is proposed with the collection of multi-source heterogeneous big data, explorations on the impacts of driving behavior, vehicle design, travel patterns, and route choice, etc., on emission levels from urban road freight can be conducted. Then, with proper freight operations models and emission models being developed, strategy evaluation could be done. Since with those data and analysis, we could understand where the city is in terms of freight, what kind of movement is happening, what kind of vehicles are moving goods, and how they move between origins and destinations. That's where the baseline setting comes into picture. Moving forward, we then can try to justify green solutions according to a low carbon target scenario. We apply this framework in the UK case study of London Lorry Control Scheme. This scheme was launched in London in 1985 for the restriction of the movement of heavy goods vehicles. And the main purpose at the time is to limit noise impacts on residents. However, since heavy goods vehicles are restricted to a core network of routes during the policy effective hours, as is shown in Figure 1, they may incur extra mileage. Thus, more emissions out of the hours will be happen. And our study supports this hypothesis. That is, additional vehicle mileage and fuel consumption are found for the analyzed company, and average vehicle driving speed is higher, and more arterial roads are used during the LLCS hours. The longer routes and less fuel-efficient speed together led to more emissions in certain areas of city out of the policy effective hours. And this is shown in Figure 2. Another work is based on the data from one of the largest freight sharing platforms in China. On this freight sharing platform, shipping requirements are brought together and jointly addressed so that vehicle resources are fully utilized at a higher level of convenience and flexibility for the connection of a shipper with a carrier is guaranteed. We would like to see whether changing freight sharing operations can lead to different carbon footprint on the road network. And current analysis results show that there are spatial and temporal variations in average trip speed for vehicles with different work status, and it is illustrated in Figure 3. Since CO2 emissions in gram per mile is closely related with vehicle speed, suggestions on demand management in terms of shifting delivery time window to less congested hours are made. Based on real-time estimation of carbon emissions for its freight operations, it is suggested to leverage pricing strategy for coordination towards a demand-supply balance to mitigate unnecessary distance traveled, so less emissions. As the closing mark, I would say that urban road freight transport does play a crucial part in carbon reduction, with more focus on sustainable road freight transport through close monitoring of road freight carbon footprint and quantitative evaluation of proposed green solutions. A more environmentally friendly urban transport management system and a healthier living neighborhood could be fostered. In summary, researches and studies in sustainable urban road freight transport help the different stakeholders better understanding the pros and cons of relevant policies, offering the opportunity to achieve the overall carbon reduction goal in a more efficient way. And thank you very much for your attention, and that's the end of my presentation. And thank you very much.
Thank you very much, Suchi, for keeping the time and very Very nice presentation, and see a lot of progress with your research for your towards your PhD. I think our time is fairly limited because there's another concluding session. We'll start in 10 minutes, so so we have to finish our question and answers discussions within 10 minutes. Now, we'd like to open for the floor for the platform for presentation for the question and answer and as any exchanges of ideas and discussions. Go ahead if anybody would like to speak anything or any comments. Well, no one seemed to be raising hand. Let me first take advantage as a chair. Would like to ask Professor Prost about your manufacturing of 3D printing of wood composites. That's very impressive research, very interesting. Maybe definitely would like maybe in future we can collaborate because here at the UIUC, Zhejiang UI, we are one of our focused areas on bamboo composites, bamboo-based. Maybe we can collaborate.
We haven't tried bamboo yet. We worked on hardwood and softwood at the moment, and so we work with pine tree and some also macadamia nut shells as well that we have recycled. So it'd be interesting to try different type of wood and see what we can do.
Sure, definitely. Actually, in Australia, there are quite a few bamboo forests too. Well, small forests, not too much. I've been to one.
Not where I am, but yeah. We have a lot of eucalyptus, so we're using eucalyptus tree as well.
Eucalyptus trees in China is popular too, and they imported from Australia, I believe. Yeah. So anyway, for other details, maybe I will email you.
Yeah, you can find. We had a few publications and a book chapter as well. Be interesting to continue this work.
Sure. So any other? Let me just start. Any other questions and discussions from the floors, from the participants particularly, and other panelists? Christopher, you seem to be too serious. Smile, I like your smile.
Yeah.
I see there's a Q&A here. There's a few questions for Professor Santana in the Q&A.
Okay, I can see the questions here. So one question is the concrete alternative compatible with the 3D printing methods described by Professor Prost? Now, of course, concrete is also getting 3D printed. So one way to reduce the amount of material that we actually use for construction, 3D printing is suggested as one way to deposit concrete only where it is needed. So I'm not quite sure. Because, of course, when we're talking about wood-based composites, it's a little bit different as compared to concrete. The application strategy is similar, but I think what we want to do essentially in both these cases is minimize how much material we're actually putting into use. I don't know. Is that fine, Gwenelle, from your side? I'm not very
sure. We do have equipment to do 3D printing of concrete. Like we have a paste printer in our laboratory. So it's like changing the composition. There's a lot of work to be done because like the fluidity of the concrete has to be quite different when you do a traditional technique of placing the concrete in place versus 3D printing. There is change of composition to be looked at. We have some projects looking at that. For the moment, we have a small printer, but we're looking at buying a bigger one.
We've been doing some 3D printing with concrete here in terms of larger scale facilities like a house, or we've also looked at a ground plus one story structure. But yeah, I mean, the principles are similar. We are doing additive manufacturing, but I guess the application is a little bit different as compared to the wood-based composites. The other questions relate to CO2 used in Solidia. I know that there's a lot more information there. Probably you can visit the website of Solidia Cement, and that may be able to give you the actual details about the amount of carbon dioxide that can be actually captured with Solidia.
Sorry, from admin level, they are asking us to stop the session as quickly as possible. Can we just maybe feature one question and answer? Maybe just in case if we are stopped, please pardon us.
Well, thank you, everyone. What an incredible 2 days. And thank you, Professor Shao, for keeping the last session on time so that everyone had a chance to take a break and then come back for the concluding session.
Hi, Professor Catherine, please unmute yourself. We couldn't hear you. Sorry. Thank you.
It says I am unmuted.
I think we can hear you quite well.
And we can hear you, yeah.
Sorry, going on. Thank you.
No, we don't hear you anymore.
I haven't speak.
Okay.
Spoken.
I think we're set now. So, as if we're all novices at this technology, which we've been using endlessly for 2 years. But it was a very extraordinary 2 days about such a critical issue facing the whole world. And we managed to get together, all of you working behind the scenes, managed to get together the brains trust, the intellectual power from some of these critical universities, the key universities across 4 continents, or 4 nations. So extremely impressive. So what we're going to do now is ask the key leaders in each of these institutions to sum up and bring some of these ideas to conclusion, because we do anticipate following up. We expect to follow up. It's not just a lovely conference. This is building on the establishment of the relationship originally between Zhejiang University and Sydney University, and then bringing in NUS and bringing in IIT Madras to build on the work that those original collaborative researchers were designing, and then building on that, and they agreed to have a conference just such as this. And just for your information, before I hand over to Professor Xiaoyang, is that yesterday there were more than 1,200 people attending this conference online in all sorts of different ways through all the different social media platforms. And we know some of the data from today, but certainly it will easily surpass 2,000 participants. So this is a massive audience. So all of you who spoke, thank you and congratulations. But you've had a bigger audience than you would ever have had at a normal conference. So we need to be able to take this further. So I'm very pleased first to introduce Professor Xiaoyang, who needs no further introduction because he's just chaired the last session. So your observations would be extremely valuable. Thank you, Professor.
I'll just mute myself. Well, thank you very much. And I was just trying to ask our staff what my role would be, what I should do. Very much interesting to participate in this symposium. And I think one of the most important things to knowing people. I prepared a very short PPT. If I can I share it? So can I just, if I can you see my presentation?
No, and I can't help, sorry. It'll have to be one of the support people.
Can somebody allow me to share the presentation? It said I can. Stephanie, can I share my screen?
It's happening now. It's starting to screen share now.
Oh, okay. Can you see my slides? I assume you can.
I think
yes?
they're still loading up. It says you've started screen sharing, but I have a black screen. I don't know about others.
It's probably take a few seconds to bring it up.
Got it now. We can see it.
Okay, all right. So I mean, just maybe 4 slides, just some research activities, sustainable systems we're doing towards a carbon neutral society. And I would like to emphasize this is society because although we are, I'm at least my side, we are engineering professors, I think, but we need to emphasize this societal impact and also studies. So that's something. In terms of sustainable systems, what we're doing, I think we should address the sustainable systems from 2 different scales. One is macro systems, like a global ecosystem, ecological systems, like a global weather, global the ocean aquifer studies, and also we traditionally, most of us are working, particularly from engineering, we're working from the micro system side, like one building, one industry, even a specific materials, a specific manufacturing processes. But there's 2 levels of studies and research and also approaches are necessary. Another thing, when we look at the sustainability, I think we should look at that as a time function. One is we should look at the short-term effect, like instantaneous event or effects. So I call it the delta T. So like a natural disaster, like an earthquake, a typhoon, or social impact like 9/11 or COVID-19, these are instantaneous or short-term effect, but they have a destructive effect on the sustainability. So just like a building, if it is destroyed by earthquake, then it's not sustainable at all. And certainly the other side is durability. The long-term effect, like life cycle effects and the durability, etc. So these are a few different views I think we should have. We are kind of working on trying to develop some sort of index systems that can include everything in it. But I think this is maybe just a conceptual. And like look at the time effect, the durability, like the summation of different attacks from an extreme event, like an earthquake, because my background is earthquake engineering, like we want to look at the several sequences of earthquake attack, like aftershocks, the effect on a building. So that sort of things. Just a few examples of our current activities. So, for example, one of the recent activity we organized is the first international competition on modern bamboo structure building design. This is a kind of building design, including architecture and also structure design for using bamboo as a modern material. I think there's a team from Sydney student attended this competition, and the result will be open pretty soon. Another activities we're doing at the Zhejiang UI Institute is use glue the laminated bamboo to build the buildings, structures, bridges, etc. This is a building we just built last year, and this is like in winter after completion. It looks like a timber building, but it was built with bamboo composites, and certainly with some recycled concrete. If I can summarize some of my hopes for next steps towards the collaborations, I think maybe we can look at some joint curriculum, and certainly student and researcher exchanges, and collaborations in our joint research programs so that we can together target some opportunities at different in different countries, and then we can form some focused joint research projects and workshop and groups to address some of the problems related to sustainability and carbon neutral development. Thank you very much, and thank you for the opportunity to be here.
Excellent ideas. Thank you, Professor. Very exciting for our students and our researchers. So there's some great ideas. I'd now like to ask Professor Huang Jun to give his overview and summing up and ideas. Thank you.
Thank you, Casey, and also thanks colleagues from all 4 universities to give a fantastic presentation and introduction of our efforts and research outcome in the sustainability. So it's obvious the sustainability is a global challenge and become our research focus for each university. For the senior uni, so in 2018, so the senior nano start grand challenge. The CO2 zero is one of the grand challenge project in under the senior nano, and we are have 15 research groups across 6 schools. We started this kind of internal collaboration, and then in 2021, we worked together with Zhejiang U based on this grand challenge. So we expand the internal collaboration to the external collaboration with the strategic partner, Zhejiang Uni, and then we build up the joint lab in the sustainable environment. So you can see, so this is from a seed, now it grows to a big joint lab, and now this platform, together with the 2 partner universities, so we are able to communicate and with more universities and more like partners in this area. So this is great. Especially, so this symposium provides a platform not only for senior professors and also for the ECR and also for PhD students, so to communicate their research progress and also some projects more attract more research interesting between the universities. So I think this is a very nice and a very great and timely symposium to put all us together. So we will find from the small, and then we can become bigger and bigger collaboration. Especially, we are able to put our efforts together from the collaboration with project, from the student exchange, and from even student staff exchange. Even we are able to share the facility. This is also important. So from the presentation, we find different, each university have own the research strengths, and therefore, if we are able to work together, so definitely we need to work together for this global challenge. Therefore, we are able to solve some like a grand, especially some difficult like challenges in the area. So I'm quite looking forward. So based on this symposium, we know more about our research and looking forward for the further close collaboration. And especially, we already have a close partnership with Zhejiang U for the Sustainable Environment Lab. And based on that, and really welcome so 2 partner universities like NTU and IIT, NUS and IIT join us and to make more fruitful for this collaboration from based on this platform. And thank you.
Wonderful. And now I ask Professor Lo Wai Lam for his observations of the 2 days and where to from here, some good ideas. You're on mute.
Sorry. Yeah. So first of all, I'd like to say that the recent pandemic has actually caused a lot of conferences and symposiums to stop working. But then having said that, this hasn't stopped us. I mean, this hasn't put research collaboration in the back burner, but instead, with modern technology, we are able to have virtual symposiums, virtual conferences. And in fact, this has even opened up bigger opportunities. If you have a physical conference and symposiums, then you need have only certain number of people attending it. They have to travel many miles to attend the symposium. But with virtual symposium, you are able to bring people together. For example, Catherine earlier mentioned that we have more than 1,200 people attending the conference, this symposium virtually. I think that's a good news. I mean, for a physical conference like that, I mean, we may not get that kind of numbers. But in this case, we're getting more people to listen to us. And also, this opened up for more cooperation and collaboration opportunities. throughout these 2 days, because we have actually heard from various universities what are their perspective towards sustainability, research, and then of course it allows us to actually understand each other better. So from there, we can actually interest colleagues to work with each other, because research alone, we can only do so much. But if you do collaborate with people, you can do a lot more. And this particular symposium also bring together not just engineers, but also engineers, chemists, designers, architects, even transportation all together to address one single problem, which is carbon neutrality. This is something that is quite close to our heart, because we need to make sure that we will not get too burdened by CO2 in the future. So this allows us to actually explain what we are doing. And also, I'm quite glad to see that my colleague, Professor Pravin Linga, is already collaborating with Professor Rajnik Kumar from IIT Madras. So that's a good sign. In fact, Professor Pravin was telling me that he had to leave early because he had another meeting later on. But then he told me, don't worry, any questions, Professor Rajnik will be able to answer for me. In fact, this is a good sign that they're both collaborating very well. So this is a good sign. Of course, what we hope to do now is actually to open up more opportunities for colleagues from different universities to talk to each other, and then to get to know each other, to know each other better, and then we can start collaborating. I think that's a good sign. Yeah. So I think we hope to see more of this in the future. Of course, we hope to actually involve more students as well, because students are our future. So if we can get more students to listen to it, the more the better. So from there, we may interest them into these areas, and then they may become our colleagues one day. So with that, thank you very much for having us.
Thank you very much. Excellent points. And our students are definitely the future.
Yes.
So Professor Santosh Kumar Sahu.
Yeah, thank you very much. I just want to share my screen if I'm allowed for a few minutes to discuss about the takeaways of this event, which has been wonderful gathering of researchers, academicians, students, and all of us from last 2 days. It's been a wonderful symposium of exchanging of ideas, and I first try to put forward what IIT does, IIT Madras does, in terms of achieving the carbon neutrality by 2050, and these are the number of activities that IIT Madras does in terms of developing technologies, educating students, and engaging them to understand the impact of global climate change. Having all these areas, it is interesting to note, in fact, in the last 2 days, that this is what I understand from the engagement that we have so far. So we talked about education and research, we talked about R&D technology and innovations, and we also talked about policy and implementation. This becomes a larger challenge for not only India, but also for all of us. That needs kind of a starting point from educating our youngsters to creating basic research, R&D and technology innovation, sharing ideas, and then pushing forward for a larger policy implementation for a better future. Now, having said that, I just classify them into a few points. First is on education, what we discussed. The interesting thing started by Professor Raghu of IIT Madras was how we can move from campus to local to global initiative on carbon neutrality, micro studies as spoken already by my previous speakers, to making it a macro study so that we have a possible impact on reducing the impact of global climate change. Specific focus on sustainability education focused by energy science, energy engineering, carbon finance, carbon neutrality studies would definitely add value to all of us in terms of educating the next generation. Of course, in this line, Energy Consortium at IIT Madras is trying to collaborate with students, academia, and industries to kind of get the best in terms of not only research, but also in applications. Looking forward for R&D technology innovation from all the speakers putting together. We discussed role of hydrogen, a highly discussed topic. Innovation is required to make us energy efficient, smart, sustainable building networks, sustainable nanotechnologies, climate solution related to energy and climate policies, which are highly important at this point of time to do a multidisciplinary research to focus on the policy in such a way that we achieve the goal at least by 2050. Moving forward, we also discussed urban heat resilience, energy water nexus, rainwater harvesting as largest area in last 2 days of the deliberations, which I'm really happy, and I learned a lot from the deliberations. Moving forward, what we can do is one of the questions that we always ask, we can exchange ideas. I exactly echo with my earlier panelists who are kind of okay in terms of collaborating research, academic and industry research together, identifying new research domain, multidisciplinary, transdisciplinary domains where we can work together to come up with different ideas that can help the economy grow faster. Of course, in this particular event, we need academic and industry collaborations that would help not only understanding the industry problem, but also put forward the academic knowledge into the development of industries. Of course, nonetheless, we are all interested in a better policy dialogue that can basically help, the international agency to kind of deal with the global climatic problems. Thank you very much.
Wonderful, thank you, Professor. So, thank you all to my very esteemed panelists for sharing your observations. As they said at the opening of this symposium, we're facing the most critically important of issues, and just hearing those discussions and the work that everyone's doing and the creativity, it brings optimism to our future, and particularly those PhD students. Extremely impressive work, and it's wonderful that they had the opportunity to showcase what they're doing, because it's extremely impressive and possibly more creative than us who've sort of been around for a day or two, maybe. So now what we need to do is you've put together some ideas, collated and synthesized the observations. Now we have to turn it into steps. So you've presented some specific ideas, but we need to now turn it into what we're going to actually do. And so there are things like grants from each of the countries, as I understand it, to support particularly students, early career researchers, but to take these ideas further, to collaborate further. And I think that, that there is an agreement to get together to debrief after this event, so that go away, think about it, think about who to further engage in all these ideas. And then the officers at each end of your universities will help to turn that into actual action. So I'm really hopeful. Thank you to everyone. Some days it doesn't feel so hopeful, but particularly our PhD students, it brings an awful lot of hope to us. So thank you to everyone, to all the presenters over the 2 days, to all the massive audience around the world, and also particularly to our, as I said, esteemed distinguished panelists, bringing those ideas and synthesizing them so that we can turn them into what we're going to actually do to achieve something in this really dramatic space. So thank you very much. And I think that's the end of the session, but we'll all go away with so many more ideas, and having met people virtually at least, so we know who to reach out to. So thank you all.
Thank you very much.
Thank you
very much. Yeah. Bye.